we have part 2 of building an ESC from scratch. So we are going to continue where we left off on the other video. On the coding section, we're going to be using the same layout on the breadboard. So if you watch the first video and continue on this one, you won't be missing anything in between. My setup remains the same. I have my motors ready for testing. I have this, by the way, this is by far the easiest one to develop for because it's so smooth. The magnets are not strong and it's only 900 kV. I have 7 motors in total. So I have the 900 and I believe this one is 1200. This one's a little more difficult to develop for. And then on the back, I have really fast ones, 4600 kV zinc motor with a 2.5-inch prop. And then we have a 2600, so this is a 26. And then we have 3500 with a 4.5-inch prop. This is a little difficult to drive as well. And then we have one with a dual shaft with very strong magnets. It's hard to turn. And then one more 46, stronger magnets than this one, more difficult to drive as well. And my setup is the same as what you saw in the picture. Right? Obviously, I'm going to be including the link of where you can get the list of all the components, quantities, and everything needed to build this. So I have everything ready to go. My data sheets for the STM32G0X0 reference manual. I have 4 copies here because I'm going to be using different registers and I don't want to be jumping back and forth. And then this is the code. This is where we left off on part 1 of building an ESC. So step number 1 is going to be to configure the processor, all the inputs and outputs, all the pins pretty much. So let's migrate this because it's a new version of STM32. Okay, so here it is. So if you saw the last video and let's see, when I went through all the connections, how all of this is connected to the processor here, we're going to configure all the pins to match the layout we have here. So first, we're going to need this for debugging. And this is just going to be an output pin, and these 3 are going to be the external interrupts for zero crossing. We'll include one more pin here just to add the capability to reverse the rotation of the motor. So this will be an input, and then this will be the the output disable for the MOSFET driver. And so these are going to be outputs, 3 of them, and the PWM lines. These ones are going to be on timer 3. And the last one. Now I'm just going to go label them. So we'll call this one LED. 0 crossing _A, B, and C. We'll call this rep. Output disable A, B, and C. That should be B. So you can see that the names match, at least on the ABC, so those go together. So when I start writing code, I can keep track of what I need to change. So that's it. Those are the labels I need. So now I can go and configure my GPIOs, and I'll start with, well, yeah, I'll have that one as pull down, and then those three need to be pulled down as well, and the zero crossing ones, this is important, they have to be pulled up, and they have to be external interrupt mode falling. Okay, if you select any other, there is a chance that it'll lock up and it'll never start. Obviously you can add code to compensate for that, but it's easier just to say falling instead of rising, or rising and falling. Okay, so that's it for now. We're going to come back to this later. Let me just disable this here. We don't want to force DMA interrupts because we don't need it for everything. So now we'll set this is the most important channel. This is the one for driving the MOSFETs. So we did 2, 3, and 4. So we'll do 2, 3, and 4. It will be center align mode 2, and the resolution will be 10 bits. So 10 to the 4 minus 1. We will add 3 DMA channels. And they all have to be memory to peripheral. We'll set them to very high. And we want all of them circular mode. So they are all circular, and they have to be a half word or 16 bits. So that's it for those. Want to make sure this is disabled. We'll go to GPIO settings, and we want those to be pulled down. So we have that. We have the DMA that is disabled. Center align 1024. We should be good to go. We're also going to use timer 7 just as a general timer for pausing, and also to keep track of how long we're doing something. That's it. No changes here. And we're going to use timer 17 as an output compare without any output, and we are going to have interrupts on this one, and we're going to use this to bump the motor if it's not spinning, just as a way to keep it from stalling. So this way it will always be in closed loop mode instead of having a routine to get it going. This will do it for us. So we're gonna change the prescaler to 64,000, so that means that we get 1 second before it counts to how do I say? This will give us 300 milliseconds. So every time it goes through here is 1 millisecond, right? So I think it's 1 millisecond. So this will give us 300 milliseconds. So if in 300 milliseconds nothing happens, it will bump the motor to get it going. And we're also going to set the counter here, the pulse, to get 150, but that's going to be in code. So it's just a way to keep it running. So we have the interrupt going. That one too. And let's go visit this again, make sure everything's configured. So we need to enable the external interrupts for 9, 14, and 15. And you can see this is the external interrupt for lines 4 through 15. So we need this. for the zero crossing. This looks good. They're all pulled down. Those are the PWM lines. And then, so, alright, they're all pulled down. This one's are pulled up. We are going to change this. This is the zero crossing. I'm going to change the parameter to 1 instead of 0. Isn't that as important? This one is really important. This one has to be available all the time so we can control the speed of the motor. So that's it. Let's generate the code. Okay. And we have 3 additional timers now. So put it here, and if you upgrade it to the new Cube IDE, you need to put this in front of each of the lines. For some reason it's not recognizing this. So let's make sure it compiles. Thus. And alright, so what do we need to do now? Well, let's start defining what we need. So we're going to need a handful of functions. I believe it's 5. So first we need a way to set the speed or the duty cycle. We also need a function to commutate the motor, and we need a couple of, well, we need to detect the zero crossing, rising and falling, so that's external interrupts. So we'll go get those, and make the code a little bit bigger. They should be under GPIO. Callback. There we go. This too. And we also need one more interrupt on the output compare timer 17 for bumping the motor. So that will be on the time header. And that one is that one. Okay, so those are the 3 functions, the 3 interrupts we need. So so once we have all of this, obviously we want to initialize the timers, and we have to actually, before we do that, let's just start writing the code here. So first, for setting the duty cycle, let's define another motor speed current. This is just so we don't increase the motor 100% from 0 to 100. We want to ramp it up nice and easy. So what we're going to do here is check if motor speed is not equals to motor speed current. Then we check to see what the difference is between motor speed current. So if it's more than 20, then we can say motor speed current 20, else Okay, and then we can set the duty cycle. Okay, that should give us a way to call the function only when the speed is different, so we don't keep calling this function for no reason. And if the difference is more than 20 points, then we'll increase it 20 points at a time. Let's do 10 instead. So now let's define this. Obviously, we want to check for DC to not be more than our 1024 resolution. And once we have it set, we can specify the DMA buffer. We are going to be using PWM, but we're going to control it via direct memory access, or DMA. And we're going to be using only one buffer, so I'm going to get it ready just in case we do dithering. I doubt that we're going to get into it, because this video is going to be about 90 minutes long. So we'll just leave it at that, and then define what we need for this to work. So we need a 16 DMA pulse, so it's going to be only one, and DMA pulse reload. So this will be the resolution per pulse, and we said it was going to be 24 or 10 bits from 0 to 24, or 0 to 23. We'll leave it at 24, doesn't matter. And here we want the buffer pulse will be 0. Resolution okay, so that will work. Next will be this one. So this one is a little more involved, so let's see what we're trying to do. Well, actually I don't need to do that. I have it ready in another page right here. So these are the steps. So the steps are from 0 to 5, or 6 steps. I just have those extra ones to illustrate how this works, how the commutation steps go. So we have, those are the first 6 steps for the high side, the floating side or off, and then the low side. So if I select any of those, you can see how it goes. Right, so it starts high, then it goes floating, then it goes low for 2 cycles, floating, high 2 cycles, and it goes up and down. So all of them are the same. Right, so that's what we're trying to do. So in order to commutate, we need to disable the interrupts. Right, so that's the first thing. Then we need to, well, first we need to clear the wake up with interrupt register, then disable the interrupts. Then we clear any pending interrupts, and that way we have it ready to commutate. Now to commutate, we want to check if the floating side is going to be rising or falling. So for instance here, or in step number 3, if you will, right here, B just came from high, and now it's going to be floating, but it's actually going low, right? So it's floating and it's on its way down. So it's going to cross 0 from positive to 0. And then 2 steps after, or once it goes low, well, actually, let's do this one here. On step number 4, A just came from low, now it's floating, but it's going up. Right? So let's write the what we're trying to do here, so this makes more sense. So first, we want to clear the wake up interrupt reg. Then I'm going to disable 0 crossing interrupts. Then clear any 0 crossing pending interrupts. And now that we have it ready to commutate, we want to increment the step or go to the next step. So go to next step or power step. Right, so that would mean that if we're on step number 2, next step will be number 3, right? And once we have that, now we have to check to see if the next step or the step that we just went to here, is it going to be rising for the floating phase? This would be your floating phases. So if we're on number 2, this is the one that is floating, so that one is rising, right? But on step number 3, B is falling. So we need to check if a zero crossing is rising, then we do something here. So what do we do? Well, we enable the zero crossing interrupt on timer 3. Yeah. Rising interrupt for timer 3. And then what will we do next? So we are on 2, right? It's rising. That's what this is. If it's rising, so if it's rising, let's assume that we're on step number 2. So we are here, which means that now we have to disable, because it's rising. Prior to that, it was low. I'm sorry, take that back. So this one is rising. So we're going to disable this phase, C, but A was floating on the previous step. So if we look at step 2, A is now low. So we have to enable the output disable low when it's rising, and vice versa when it's falling. So enable output disable low. Else enable zero crossing falling interrupt. So it's just the opposite on than the previous one. So enable output disable high. And once we have that, now we can go ahead. We're still on step number 2. Now we can disable that phase, C. So it used to be low. It doesn't matter what it was, if it was high or low. We have to disable it. Right, so disable output disable, or disable output disable off. Right, whatever's here. Then we check to see if it's falling. So we're going to do something similar to here, but now we're going to disable. We need to disconnect the DMA and disable the capture compare as well. We're just kind of doing a workaround, so we don't have to do a lot of changes of registers and how the pins are configured, because that takes a lot of time, and we're trying to optimize this code as much as possible. So if it's falling, we want to disable, so the high side, this is all about the high side. So now if we're on step number 2, right, if it's falling, actually it will be number 3. If it's falling, we want to disable the PWM side of it, or the DMA on the high side on B, right? So we're falling, B was on PWM mode, so now we want to disable that part. So we want to disable the capture compare on timer 3. Actually, this is not on timer 3, this is on the external interrupt. And disable DMA on timer 3. Else we do the reverse. So we enable CC on timer 3 and enable DMA on timer 3 as well. right? So these steps are gonna be, this ones are done. You know, if it's on this one, if it's falling, let's say it's this one, right? If it just came from high, we have to disable it. But it's on step 3, so now it's on the off rail, if you will. Once we have that, we pretty much are done doing the commutation. Now we need a delay, about 2 microseconds. The ringing on the motors is about 2 microseconds whenever you commutate, so you want to avoid it. And you know, we just add a delay of 2 microseconds or microseconds. Now we enable the wake up with interrupt again. That's what we disable at the beginning. And we are going to reset the timer 17, the one that gets triggered here, to pump the motor. So every time it goes through this function, it's going to reset it. So if there's lag in between or it's not rotating, it will bump and then come here and bump again. Timer 17 for pump motor. Okay, so that's what we need to do here. Right, so let's add some code on this, on the bump side of it. So we'll say if h time equals 17, we also want to check the active channel. Channel 1. We also want to make sure that we're actually wanting to spin, so there's some speed on the motor, or we have set the speed properly. So if motor speed current is more than 0, then we commutate. Right, so every time this gets triggered, it's going to make sure that it is timer 17, and we do want to spin the motor. And if we do, then that means if this got triggered, it's because the motor is not spinning, and we're going to bump it by calling that function. So now let's go here. Let's start adding the code for each of those steps. So first thing, we want the external interrupt, the IMR. So I'm not sure what that stands for, but let's find out. Is the wake up with interrupt mask register. So I guess this IMR. And on this one, so these are the bits that we need to change. So we have from 0 to 15. So this actually represent the pin. It's also the same as the interrupt. So we go here. You see this one's 9, 14, and 10. So it's 14 and 15. So it's 15, 14, and 9 right here, I think. Anyways, so what we need to do is we could simply set it as 0, but you know, just in case we add more functionality, we want to keep track of what the default values were, so we can always reset them. So we'll create a variable IMR flags, and we'll set it there every time it comes here. So we want to make sure this one has the reset value. And we will set that on the setup function here. And we'll clear the bits. This will be the 0 crossing pins, so it will be A. So C and B. And IMR reset flags. Okay, so that should work. Now we want to disable interrupts. EXDI. So so this is the falling, and then we need to do the rising as well. Let's see what this ones are. So this is the falling pending edge. Oh, this is not the right one. So this is the pending one. That one. Let's see. Oh, did I get the wrong ones? I had the right one. Falling trigger selection. So I had the right one. So that's the falling trigger selection. And we clear them the same way we clear this ones. So we are going to clear 15, 14, and 9. So we'll just get whatever it has and clear it. So crossing pin A, so crossing B, and crossing C. We'll do the same for the rising. Now we just need to clear the pending interrupts. And I believe rising pending interrupts. Yeah, same thing. So these are the registers, and obviously if you want to see what it does, you can just read this. Obviously to clear it, you need to write a 1 to it. So what I'm doing here is I'm taking the values of this and doing an N against these values. So if it's 1, it'll write a 1 back to it and it'll clear it. On this one is the opposite. I'm getting the value, clearing the value, and then writing the whole thing again. So there you go. Now the power step, this should just be a variable we're going to increment, and also we want to cap it at 6 steps. All right, so let's define this. Okay, and then let's define this. So if rising, so how can we detect if it's rising? Well, we need an array that can be indexed with power step. Right, so this array, so it's going to have these steps, and if you want to know if it's rising or falling, or you look at the off one, and you know that this one is rising because it's going to go up, and then the next one is falling because it's going to go down, and then the next one is rising. So if it's either rising or falling, it's alternating back and forth. So we're going to start with rising because it is rising. It's going to be 1 0 1 0 1 0. So let's define that. Rising, and it'll be 6 steps. 1 0 1 0 1 0. So there. Now we'll know if it's rising or falling. So once we have this, now what we have to do is just this. Right, we'll bring it here. This is the rising, so we'll change this to R. And now what we need to do is we need to specify which pin. Right, we can't have all three, so now we need another array here. So we're just gonna call it off, zero crossing off. We'll index it with power step. So let's go create this array. It's gonna be 6. And this is just pins, right? So which pins are we doing? Well, we're gonna do the off one, right? So it will be BAC, BAC. So it will be B. So it'll be BAC, AC. So those are your BACs. That one's taken care of. Next one is setting the OD low. So what does that mean? It means that this one of this is going to be set to low, and this is for the well, the low, right? So this is the low. We're going to need an additional array, and it's going to be CC, AA, and BB in that sequence for these pins down here. So we'll go here, and forgot, they are all on port A. So GPIO A, ESR, and we'll say output disable low. It will be an array indexable by power step. So let's go create this. Unit 32, 6. And this is pins, so we say it was going to be CC, A, and B. So CC, A, and B. So that's taken care of. Now we do the same here in reversed. And this one's going to be for the falling. So that stays the same. This one will need a different array because this is on the high side, and we'll just call this high, like that. So let's go copy this one, rename it, and for high side it's A, B, B, C, C, A. So A, B, B, C, C, and A. Okay. Next, we need to disable on the floating side. We need to disable the output disable pin. So same GPIO A, BRR, output disable off, power step. Just one more array we need to create. It will be a copy of this one. Off. And for that one, we need this row. So BAC, 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 BAC. Done. So now we need to do something similar to this. So if it's falling, power step. and we do something, else we do something else. So here where it's going to be timer 3, yes, timer 3, and this is the capture compare enable register, that's what that thing is called, and we're going to clear it. Now what do we need to clear here? Well, let's see. So this is that one, right? And so you can see that the CC number E is the capture compare, and then the channel output enable. So we're looking for CC number E. So we know we're using channel 2, 3, and 4. So here's 2, 3, and 4. So it's 4, 8, and 12. And this is going to be for the floating side. So that means that we need to do BAC. So this is B, A, C. So we need to do 8, 4, and 12. That's how the array needs to be defined in that order. So let's go here, and we'll call it CC off power step. So 2, 6, and the second one's going to be 8, I think. B. I think I had one too many. So BAC, BAC, it's going to be 8, 4, and 12. 8, 4, and 12. Let's verify that. So 8 for 3, 4 for 2, and then 12 for 4. So that is correct. And we also need to disable the DMA. So timer 3 again. So it will be the DMA something interrupt, I think it's called. So let's call it DI off power step. Let's see what this one requires. DMA interrupt enabled register. So same as the other ones. So we're looking for channel 2, 3, and 4, right? So we have 2, 3, and 4. So we have 10, 11, 12. And because it's going to be the off channel, it's going to be BAC, BAC. So this will be A, B, and C. So it's going to be B, A, and C. So 11, 10, 12. So we can go back here, copy this one, call it DI, and we say it's going to be 11, 10, and 12. 11, 10, and 12. So it is, so 11 for 3, 10 for 2, and 12. 11, 10, 12. All right. That should do it. Else, if it's rising, we want to enable it. That's it. So next, we add delay, so we'll use timer 7, reset the counter, and then do a loop while timer 7 counter is less than 128. If you remember, the processor is running at 64 megahertz, so 64 or 128 is 2 microseconds because it counts, the clock runs 64 times for every microsecond. So this will make it 2 microseconds. and then we'll enable this guy here, which is what we disabled before. We're just gonna add the zero crossing off pin power step, and that will enable the wake up on it with interrupt for the floating side. So essentially it enables interrupts. And then last, we'll enable or reset timer 17 counter to 0. So if it says reset, if it gets reset to 0, then this doesn't execute, right? As long as we keep resetting it before it reaches whatever time we decide to set it to, then it won't bump it. Okay. So now let's add some logic to these two functions. It's going to be identical for both. So we'll use timer 7 here as well. Reset the counter, and then we will loop. Well, timer 7 counter is less than what? So let's put the full resolution plus 1 microsecond minus the motor speed current. So the faster we're spinning, the less we're going to check, and the slower we're spinning, the more we're going to check to make sure that the ringing doesn't affect the interrupt. We don't want false positives. So if that is the case, now we need to check. So when the interrupt fires on one of these pins here, we still need to check to see if it's still high or low, whichever we're checking. We don't wanna consider positives when it's firing because of a spike or noise on the line, right? We want to make sure that we have a solid line. So every time the interrupt fires, we're still going to check, make sure that the interrupt is valid. So now we have to check the state of the pin itself, not the interrupt. And this one is on different ports. So this is on port B, and this two are on port C. So we need an array of ports to be able to check this. So we'll call this a port off power step, because we're going to be checking the off sequence, and IDR. We're going to end this with the off power step. So if it's rising, we want to make sure that this thing is high. But if it's 0, that means that it's not valid. We return. Otherwise, we commutate. We're ready for the next commutation. And we'll just copy this down here. We still haven't created this array. We still need to do that. So in this case, if it's falling, this has to be 0, right? Otherwise, if it's high, we'll return. So we'll remove this. So that way it'll check. If it's high, it'll return. If it's low or here, it'll return. So let's add this one, that array. Add it here. Constant. It's going to be a GPIO port pointer. 6 steps. And it'll be an array of pointers. And this will be the off, so it will be BAC, BAC, same as before. So this is B, not the pin, but the port. There we go. So BAC, BAC. Okay, let's compile, make sure nothing's broken. We've got some errors. So let's see. Try this again. No errors. So we are good. We're almost done, I think, because we have our interrupts ready to go. We have our commutation line function, and we have our duty cycle function. So now we just need to initialize the timers, and also initialize the DMA, timer 3, timer 7, and disable the well, you'll see. There's some tricks that we have to do in order to minimize the number of steps. So we'll do it here, and we'll what are we doing? A start timer. This one. Timer 7. Alright, so we'll do that one. If it's not equals to all okay, then we'll loop our handler. We'll do the same for 3 as well. And we have to do the same for timer 17. So all time set compare (17) channel 1. We're going to set it at 150. So we have the resolution at 300. We're going to set at 150. So 150 milliseconds before it bumps the boiler after it's commutated. So if there's no additional commutation after 150 milliseconds, it'll bump it again. And then we'll start the timer. And this was going to be in output compare. And let's see that one. IT interrupt. Alright, and it's going to be on channel 1. So that should do it. Now timer 3 is a little tricky, so we have to first set timer 3 CCR. So we're gonna set 2, 3, and 4. So we'll start with 2, set it to 0. So PWM will be at 0, so we'll always be at 0. And then we'll start PWM, start timer 3, channel 2, and right after that we're gonna stop it, but we're gonna stop it with the DMA. So stop DMA, this one here, 3, channel 2, and then as soon as we stop it, we're gonna start it. I'll explain why. That one there, 3, channel 2, and then data, and then DMA pulse. And for data, we are going to, it will be 32-bit DMA buffer. All right. So because we're only going to be disconnecting the DMA from timer 3 and disabling the capture compare, we want to make sure the PWM on the back end is still running, but it's going to be running at 0. So we don't have to keep switching the pin to high and low. So this will keep us from doing that. It will make it easier. But in order to do that, we need to set it to 0 and we need to start it. And if you stop it using the DMA, it leaves it running in the background, but the DMA takes over. So the DMA is just configured, ready to go. And then you start the DMA, ready to go. So we're gonna start the DMA on all three channels, even though this processor is not able to handle all three at the same time. We're only gonna enable one most of the time, sometimes two, but no more than two. So two is perfectly fine. So we'll just duplicate this and do 3 and 4. Same with this, 3 and 4, 3 and 4, and same with this, 3 and 4. Okay, so we have most of it configured, I think, at least it looks configured to me. And so the other thing you want to do is, because we are setting interrupts on lines that may be floating, this one's here, there is potential that it's going to be stuck in a loop as soon as you set the interrupts, and you're not going to be able to come out of it. So what you want to do is, obviously what I said before, is you want to make sure that those pins here are set to falling, and you can add additional code on the interrupts to check if it's running or not, just so it doesn't get stuck in a loop. But you know, this is highly optimized code. You don't want to add any more lines than needed. It would be here that you would check to see if the motor has any speed in it, and if not, let it get out of it. But we don't want to add any more than we need to. Interrupts should be minimum code. You know, even though we're looping quite a bit here for a few microseconds, it gets less and less the faster we go. So it gets really efficient really quickly. Now, let's see. This one here, enable disable interrupts. So because we are going to be loading code on and off, we want to make sure that whenever we reset the processor, there is a delay of 1 millisecond, and before that you want to reset this to 0. So you want to disable interrupts, rising and falling, so it doesn't spike. Your amps don't spike trying to spin the motor when it's trying to reset at the same time. So let's see if this works. Let me compile first. We got 4 errors, and it's complaining about what? Not declare. It's lowercase. Alright, no more errors. Okay, let's load it. And so here's the Beta flight connected to my flight controller. And that's not what I wanted. Let's move to this one. Let's connect it to the easiest one to spin, which is this red one here. See if it works. See if anything's broken. So I have power. Let me put it at 7 volts. 8 volts. So let's go to Beta flight. I did try to spin, but it hit the wire. Beautiful. let's move this over. Let's see. Where you go? Oh, I can't see it. Okay, hold on. Let me move this guy right here. And let me make it smaller. Wait, right here, this one. So if we move this up, oops, gotta grab it from here. Oof. Very nice. So I can spin it, stop it, spin it, stop it. Now what if I wanted to reverse it? Well, reversing it shouldn't be that difficult because we are using registers, I mean arrays. So we'll just add some code here to reverse it. So let's add a, call it reversed, make it 0, and we are gonna change this to make it a multi array. It's gonna be 2. So the first one is for going forward and the second one will be for going backwards. Oh, come on. So the difference is now it just has to be the opposite, right? And that would be for reversing and going forwards. And also we will need another power step to keep track of the actual step, because we don't know if it's going forward or backwards. So now we'll use this and change it here and say if reverse, then we want to say power step equals 5 minus power step current, right? So that's going in reverse, else power step equals power step current. That's going forward. And here we just need to say reversed. Everywhere we're using rising, so I think it's only twice. Let's compile it. 2 errors. Oh, I have one too many. There we go. So we did enable this pin for reversing, so let's check that pin and then we'll change it whenever that thing is either on or off. So let's go here to the code, go all the way to the bottom, and it is on port A as well. Here, all the way to the bottom. So here we'll say if make it direction equals 0. So if direction is not equals reverse, then I guess this would be a good place to stop the motor and spin it, but we're not going to do that. We're just going to set it to direction. Actually, let's stop the motor real quick. So we'll do this. And set this to 0. And then we'll delay a little bit, 100 milliseconds. But here we'll say if GPIOA IDR in reverse, then we can say direction equals 1, else direction equals 0. So let's see if it works. Let's compile. And we'll send it over. So once this goes, all right. So let's spin it really slow, right there. And let me move this a little bit here. Not sure if you're going to be able to see the whole thing, but I have this wire here that is connected to 3.3 volts. So if I lift it, it should stop, and it goes on the opposite direction. If I connect it again, what happens if I go faster? Obviously you can hear it cranking, so even faster. Probably not gonna like it. Stop it. Alright, so let's see if we can spin something else. So, well, yeah, let's spin this little guy here. Bring it around. This guy right here. Alright, let me lift the camera a little bit. Yep. Very nice. So let's try this one here. Make sure it doesn't hit anything. It goes, bring the camera around. There. That's as high as it'll go because my power supply only has 5 amps. and right there is 0.6, 1.2, 2 amps, 3 amps, 4 amps, and that's 5. And it starts dropping the voltage, so I don't have a powerful enough power supply to test it. But that's because it has a propeller, so because it's loading, it uses a lot of amperage. So let's try this little one right here. So we should be able to up the voltage on that one because it doesn't have any load, any propeller. So let me get 15 volts. Let's see, 19 volts. Now let's look at it on the oscilloscope and see what we get. So let me see. Do I have it here? Yeah. And of course, because I changed the resolution, make it smaller. Alright, let's plug it in. So let's see. Connect it to ground. And we're gonna check B just to see if we get something right now. Okay, so let me switch the camera. I'm not able to have both of them running at the same time, so unfortunately. Ah, hold on, just realized it's upside down. Let's see. Where transformation? There we go. It's 100%. Let me stop it. So there's the signal, right? Although that's not how we want to see it, so let's enable some debugging here. Actually, I want to. Let's see. So there's your signal. That's not 100%, so that's 100%. Nice. That's at 12 volts. So let's add one more line or a few more lines. So let's check the zero crossing. Let's see what we get there. So this right here, this is where it's detecting going high, passing zero from uh, from negative to positive, and then this is where it's detecting crossing zero from high to low, low to high, high to low. So let's see, let's add one more. Let's check the ground so we can see how the ground behaves. Pink. Let's see. To 100%. All right. So we'll align this together. This one, that one. So now you can see this line right here. This is the ground. The ground moves up and down. It's a floating ground. But you can see that right here is where it crosses from low to high. And then here's where it crosses from high to low. And if I move this up, you can see that's where it is detected, right? So this is the comparator firing going high because it crossed. And then here's where it falls because it fell down. So let's see again. Now when it's not 100% duty cycle, everything looks different. Move it up a little more, closer to 100%. So much different now because you can see the comparator firing high and then low, high and low, and you have to be able to detect it in any of those. And here's the ground. The ground, it doesn't stay high, it also drops, and then it comes back and it drops and it comes back and it drops. But that doesn't matter, you're still able to detect it. 100%. And to make it more visible, I guess, we can bring them down. Let's get this one high. Bring this one here. 2 volts right there. So there you go. Here's your zero crossing signal. This is your ground. And turn that off. And this is your what is that called? I guess 100% PWM, or the signature of your motor. So we can still drive it really fast, a lot faster, and that is based on how far this thing is from here and this to here. So as soon as this starts to go over, that's as fast as you can take it, because this is going to start coming up and this is going to start going forward. So if we go up in voltage, bring it down. So that's 15 volts. 19 volts. So you can see that there's still a little bit left where you can drive it even faster than that. But the code needs to be optimized even more. So now to make it go faster, obviously you would have to optimize it a lot more than what I have here, and that would come from here. It's likely that you don't need all of this anymore. It would be 1024 or even less, or even not even check it once you're fast enough. For rising, you will have to check for falling, because falling is more difficult to detect than it is for rising. And you could optimize this some more if you wanted to, but I'm not going to. I'm going to leave it as is. So what did we solve? Well, we can drive any motor. We can do forwards and backwards by simply sending a signal on a pin. Yeah, that's about it, right? How long is this video? Hour and 20 minutes. I don't remember what else I said I was going to show you guys, but that's about it. So configuration, very important. This needs to match exactly. We're driving everything using arrays to simplify the commutation process. So there's very little coding. Reversing the sequencing is fairly straightforward by just adding one more variable, and if we're going forward or backwards, then you just subtract, or you just set the actual step. What else? Oh, obviously, this is important as well. You have to set your PWM, and then you have to start your DMA, and then it will work. Okay, I believe that's all I have. If there's any corrections down the line, I'll just post them on the channel, but that's it. Enjoy.